Hello everyone, my name is Tong. I'm a PhD candidate from UT Austin, major in the experiment solid mechanics. And today I'm gonna show you how to use our DIC tool, pyALDIC. And you can find this report in my GitHub page, pyALDIC Tong. And so first, DIC is one of the most popular and powerful non-contact optical full field measurement techniques in the experimental field, mechanics field. And typically we have two different DIC methods. One is the local DIC, the other is the global DIC, and the al-dic is a hybrid DIC algorithm which combines both the advantages of the local and global DIC. And the pyALDIC, a new Python version of the al-dic with a new modern GUI and some optimized feature. Okay, today I will start from how to install and launch the start DIC. Here I will show you demonstrate use the VS Code terminal. So here I will recommend that to use a new clean environment. So here I already have one, so I will just activate this one. It's called pyALDIC test. Okay, so if you want to install this pyALDIC, it's very easy. Just pipe install ALDIC, then you can have it. Okay, because I already have it, so let's go. And if you want to use ALDIC, quite simple. You just use the command here, ALDIC. So let's try it. ALDIC. Okay, so this is a user interface. So if you're not using English, so you can change the language in the settings, then you just restart the software. You will see the new language here. Okay, and today we will have three different cases. So the first one is a very simple and classical aluminum dog bone shape uniaxial tension test. So first we need to import the images. So there are two ways. You can click the top left button here, then input your images, or you can just drag the folder to here. Okay, so now we have our images. Then you can check your images. You can see there's something very strange. If you look at the image list here, you will see, okay, image 1, image 1001, 101. So that's because our images are named by the natural order 1, 1, 1, 11, 21, 31. So you need to click the natural sort here. Okay, then you have the correct order. So you can double check. Okay, this is correct. And then the first step is to select your ROI, which is region of interest. So you click the here. So typically we draw the ROI on the first frame. Also, we call it reference frame. So here, we have some tools for you to plot the ROI. So here, let's draw a rectangular. Okay, for example, here. Okay, then you can see a mesh here. So if you zoom in, so here, it involves two very important concepts. One is the subset size, one is the subset step, if you look at here. If you see for each corner point here, which is DIC calculation points, and if you increase or if you decrease the subset step, then you will have a finer mesh. And basically the distance between two corners is 8 pixels here. And if you want to see the subset size, and you can click the show subset here, and then you can see there is a yellow dashed line square, which is your subset size, and the size is 41 pixel. And how to select choice your subset size and step size, you can refer to this book by the International DIC Society called A Good Practice Guide for DIC. There are more details there. Okay, for here I would just use the default 31 and the 16 as the parameters. Okay, and then there's a new feature of our pyALDIC, that is you can refine your mesh at anywhere you want to refine. So for example, there are two options, refine outer and or inner boundaries. So let's try the outer one. So if I click this, you can see for the regions near the edge, outer edge, then you can see the mesh was refined, and you can choose different refinement level. So basically here, the minimum subset size is subset step is 4 pixels here. Okay, because we don't have an inner holes or anything. So if you click the refine inner boundary, there's nothing happen. And the other way to do the refinement is you can manually draw something here. So for example, if there is a crack or a hole here, you can manually draw a region. Now you can see for this region, you have a finer mesh. Okay, so let me just click everything here, erase everything here. All right. And then the next step is choose your tracking mode. So usually there are two different tracking modes in DIC algorithm. One is called the cumulative mode, which means you compare every images with your very first images, basically your reference images. The other way called the incremental mode. That means you compare your current image not with the very first one. You can with the update reference images. So that's two different modes. So for this one, we will just use the cumulative mode because the deformation is not that large. And the other thing is the solver. So you can choose al-dic, which is our algorithm, or you can just use the very classic local DIC. So typically the local DIC will be 2 or 3 times faster than al-dic, but al-dic can provide a better resolution, a better accuracy in some cases. And the other thing is the initial gaze, which is very important for DIC algorithm. So here we have 3 different options. So the default option is the previous frame. So this works only when your image sequence doesn't have a very sharp jump or very fast shock or a large discontinuity. And the other two initial gaze method is the FFT based and the seed point or starting point method. So you can have more. You can find more details in the literature. So here I will just use the previous frame case mode. Okay, and then we can just run it. So here I don't want to show the grid here, so I run it. Okay, finished, and a new window pops out. So first I will minimize the new window, and then you can see the displacement field U and the V, 2 different variables here, and there's an option which is the show on deformed frame. So if we unclick this, you will see, if you check the displacement, you will find, okay, the background images is fixed. They are always the reference images, the very first images. And if you click this one, then you do this again, then you can see the background is changing because all the visualization show on the deformed frames. And there are some options regarding the color map. You can choose different ones, or you can change the opacity, and also you can change the color range here. You can use the fixed one or use the automatic one. And the other thing is the physical unit. So you can provide the physical unit, so that you can convert the pixel unit to the physical unit. Okay, and the next step is about the string post-processing. Okay, so for here, I will use this. So you need to go to the new window, and there are some parameters. So first is the method to calculate the string. So here we have 2 different choices. One is the plane fitting, which is one of the most popular one, and the other one is the FEM noder from Maxim, because we have a mesh here, so we can use this one. For more detail, you can find more details in the literature. And so here there's a very important concept, which is the VSG size, basically the virtual string gauge size. So for the definition, you can find it in the good practice for DIC book. Okay, so here typically the VSG size should be bigger than the subset size, and the other option is the trim low confidence edges, because when you're calculating the string for those regions near the outer boundaries, the strength there is inaccurate, so usually we will trim the edge. And you can do the smoothing, but be careful, the smoothing here is post smoothing, so basically it means you calculate the string first, then you smooth it. It's not like you smooth the displacement field, then you calculate the string. And here you can choose different string type, Lagrange. For this one, I will use green Lagrange because the string here is quite large. And then I just compute the string. Okay, then here you can different components, u, v, and the displacement magnitude, even velocity, and also the string exx, uyy, exy, even the one missing string or rotation. So here let's check the most important one, the uyy components. Okay, and you can see in the end, then you can see there's a very large, very significant string concentration area, basically, which is where the necking happens. Okay, so also we can change the visualization settings here. So this is our first case, and we have more. So the first case is a very classic one, and for the second case, which is a rotation case. So here I will show you how to use a cumulative mode. So let's go to the second case. So here this is our images, and let me drag the image, import the image first. Okay, so here is it. So first we have a circle region in the middle, and which is connected to a rotation stage, and you can see the rotation angle starts from 0 to 40 degrees. And the first step is we need to select our ROI. So here I will draw a circle here. So I click 3-point at the edge, and this is our ROI. Then let's check the mesh. Okay, so we will use the default setting, 31 and 16 here. Okay, and here let me show you how to use the increment mode. So because the rotation angle here is up to 40 degrees, if you just use the cumulative mode, the DIC algorithm will fail at the very large rotation. So here you have to update your reference images, and ideally you should provide the ROI for every single frame here, because we choose to update the reference image every frame, or you can choose every n frames or custom frames. But even you just provide the first ROI, it's okay, it still works. So here, let's try to run this case. Okay, it's finished. Then we can check the displacement U and displacement V. Okay, generally it makes sense. And if you use the cumulative mode, it cannot track the very large rotation. And because there is a rigid body rotation, so I will not calculate the strain, but if you are curious about the rotation angle, you can try it, you can play with it. Okay, then let's go to the third case. And the third case is a mathematical under the compression, uniaxial compression test. And the challenge here is the deformation is very large, and also the geometry is very complicated. So I will show you the third case. So this is our images, mathematical. So first I will import the images here. Okay, so let's check the sequence. Okay, it's correct. And because if you see here, this is very, very large images and a very large deformation, very complex geometry. So definitely we will use incremental mode. And for this case, we have to provide all the ROI for every frame, all the frames. So there are two ways. So because I already have all the ROI ready here, so all the masks or all the ROIs, they're from our developed machine learning ROI generator tool. So I will put the link on the screen. Then you can play with it. So here there are two ways to import these masks. So first you can use the batch import button here. The other way, you can go to the image list, then Control A to select all the images and right click. There is an import region of interest for the 7 frames. You select this one and you just copy the path here. Okay, and then you select all the ROI, the masks for the ROI. Okay, then you can check if the ROI is correct or not. Okay, then let's check the mesh. So because this basically most of the unit cell, they're under the rigid body rotation. So I don't need such a fine mesh. So I will use the 32 as the subset steps. Then let's check the subset size. Okay, maybe 31 is too small. I will use 41 instead. Okay, then solver, I will just use the local DIC for demonstration. Okay, and the other thing is because the interval displacement is very large. So for here I will use the FFT as the initial guess method, and also I will use a larger search range. Let's try 500 pixels, for example, and let's run it. Okay, now it's finished, and then we can check the component U. Okay, you can see generally it makes sense. It follows the shape, and also you can check the V. And if you want to process with the more string components or even the rotation angle, you can run here. So I will skip this part. And the one last thing is for the export results. So you can click here. Then there is a new window, and then first you need to select your output folder. So you can select your output folder, and here you have 4 different elements export, which are the data, images, and the animations, and also a very simple report. So for the data part, you have different format, PZ or MAT or CSV file, and the data includes all the coordinates and also displacement components, and you can select here. And for the static images or the animation, for example, MP3, MP4 or GIF, you can choose different color range or the opacity. And for the reports, which includes the parameter you used for the calculation and the with displacement or string visualization figures. Okay, so let's go back to our slides. So basically here I demonstrate 3 cases. Our pyALDIC, which is a free and open source cross-platform DIC tool, and it's very easy to use and install. If you find this helpful, you're welcome to share with your friends or your colleagues. And this is our report link here, and if you have more questions, you can just directly reach out to me. You can find my email in the report, and also or you can submit the GitHub issue. And for more discussion, you can our Discord group channel or our QQ group channel. I will put the link on the screen. Thank you.